So today I'm going to be talking about some developments in the world of dinosaurs and share with you some of my journeys back in time. So dinosaurs are one of the jewels in evolution's crown. Animals so amazing that is almost kind of beyond belief. Some of the longest, heaviest, tallest animals that ever walked the earth. Giants that had razor-sharp smiles, and armored dinosaurs that wielded bone-crushing tail weapons. Dinosaur fossils themselves are really a privilege to study, but to know that in their final encore they took to the air, well, frankly, it's unbelievable. Over the last 200 years, paleontologists have traveled the world in search of dinosaur skeletons, pretty much to most pockets of it, from the coldest depths to the hottest infernos. And this is continuing generation after generation. So sometimes, very occasionally, paleontologists, they're basically confronted with the exceptional. Fossils like this, where you actually have the preserved stomach contents, fossils that preserve soft tissues, and even fossils that preserve feathers. Birds are a type of dinosaur, a 200-year-old theory that exceptional fossils back up and support. A theory so well supported, it's kind of like gravity. That's such the support that we have. So how about with having, all the dinosaurs around and knowing that the stuff that's absent and realizing that what you had in front of you really was there all along. So having a beautiful fossil like this and realizing that what you had is that. So what is this sorcery? How could you get something so different? Well, this has to do with laser-stimulated fluorescence, or LSF for short, using high-powered lasers and shining them at fossils to make the fossils glow in the dark. So what happens is that the laser light, you shine a violet laser in a dark room, and it causes the fossils to glow, specifically the soft tissues around the bones. And when that happens, you get amazing details. And this technique has been developed by my collaborator, Tom Kay, of the Foundation for Scientific Advancement. And I've been traveling with Tom around the world, scanning specimens with lasers to try and reveal amazing things. So in the last 20 years, in actually our part of the world, in northeast China, there have been wonderful fossils that have been found. Fossils such as this one, which preserve feather and bone and soft tissue data, that has allowed us to reconstruct the evolution of birds from an ancestor shared with bird-like dinosaurs like the raptors. And it's even allowed us to reconstruct how feathers evolved from very primitive filament-like structures. As well as these fossils, others from different dinosaurs have been revealed to be early representatives of different dinosaur groups, so really filling in gaps in the early history of those groups. And one of those includes this example. So this is an early Triceratops relative called Psittacosaurus, and it lived 120 million years ago in northeast China. So this animal we've been using with LSF to reveal the most detailed reconstruction of color in any dinosaur ever. So the reason this worked is because the laser causes the skin of the fossil to fluoresce really brightly, revealing details that you can't see otherwise. So what we were able to do is use all this information from the laser and the actual muscles themselves to create pretty much the most detailed reconstruction of an animal, a dinosaur ever, from its actual physique to the actual skin patterns themselves. And what you'll notice is that the top of the animal is rather dark and the underside is lighter. So we interpreted this as being an example, a 120 million-year-old example, of countershading. So this is a very common phenomenon in the world today, whereby animals have different colors across their body. And the way it works is, in this example here with this mammal, the sun shines down onto it, and with a darker top, the sunlight lights it up. With the sun casting a shadow over the body, this lighter part then comes in shadow. So the idea is you have a kind of canceling out effect that ends up camouflaging the 3D shape of an animal. So if you imagine if there was a lion somewhere in the courtyard over there, it would have a more difficult time of spotting this animal if it did not have, if it basically didn't have this. So that's what we think we have in Psittacosaurus, but the thing that was even more interesting is the position of this coloration. So it's very low on the body, and we scratched our head and had that eureka moment when we found that this is exactly the same thing that we see in animals that live in environments where you don't have as much direct sunlight, diffuse light, animals that live in forests. So in this deer, for example, the boundary between the dark and light is positioned low on the body. So what we were able to do is take that beautiful 3D reconstruction, do experiments to simulate where would that line fall if you had a light source shining on the model, and it matched the fossil. So it's 120 million years ago, dinosaurs were doing these things that we can see if we go into the hills behind us to see the local deer that we have in Hong Kong, the small species. So yeah, that was pretty fantastic. So the other thing you'll notice about this critter, all this stuff is soft tissue, and it's scaly. Most dinosaurs were mostly covered in scales. You notice the tail, though. There's something kind of broom thing going on there. It's got these bristle-like structures. Now, from what I was saying before, birds are a type of dinosaur, and the bird-like dinosaur also had feathers. So T-Rex, believe it or not, we have examples of their early relatives with feathers as well. So T-Rex was a feathered animal. But these guys are all over here, and this evolutionary tree of dinosaurs is as such, with Triceratops being a relative of Psittacosaurus. So if those peculiar structures, what are they? Are they a kind of primitive filament-like feather? And that would suggest that, feathers evolved right at the beginning of dinosaurs, in the first dinosaurs. Are they something different? Is it actually something independent of those feathers? So that's kind of a really important question that we wanted to use the laser to shed some light on. And so we're able to create images like this, which the laser is actually able to distill out chemical information. So you'll notice that this is orange. The original color has since been gone, mostly gone from the specimen. So this is reflecting a chemical signature, and you'll notice that it's similar to this orange here. Now, this is actually the boundary of the skin, and I said that most color disappears, and that's because these black dots are remnants of melanin, the same pigment that gives your eyes and your hair their color. So the fact that these bristles match the unpigmented skin suggests that they probably have a similar origin. They probably are related to keratin. Now, we did lots of comparisons with these structures. We were really keen to find out what they were like. And in the bird-like dinosaurs, you get these primitive filament-like structures. And these structures we found were very similar to them, but they weren't absolutely the same. What we did is actually look at very peculiar structures that you find in modern birds. This is a horned screamer, and you can see why it might have got that name from its expression. they have this really strange spine on their head, which is very, very, very rare amongst birds. And this is not a feather. Everything else on its body is, apart from the scales on its feet, but this very strange structure here. And we found that those things on the Psittacosaurus's tail were very similar to it. So we kind of were like, wow, okay, well, that's kind of a bit puzzling. If this is not a feather, then what is it? So it kind of really threw a spanner in the works, and even the laser revealing these new insights, what it showed is that really we need to be finding more clues to finally resolve this debate. So, the laser at the moment is, at the cutting edge of resolving the actual physical appearance of dinosaurs. So one of the bottlenecks that we have in paleontology, it's common to all sciences, is actually finding dinosaurs. So I spend my summers in the Gobi Desert in China when it's rather hot, and spend weeks and weeks kind of looking at the ground. It's difficult to find dinosaur fossils. It's even more difficult to find tiny little animals, such as little mammals. So in the time of dinosaurs, the mammals were all pretty small, no bigger than a cat or a dog. And so that was one of the things. So as a dinosaur time mammologist, a Mesozoic mammologist, you're kind of resigned to the fact that sieving through tons and tons of material and sieving it is kind of part of the job. So that was just what people expected. And after you've sieved it, you spend a lot of time under a microscope picking through and trying to see if you might get a fossil tooth or bone. But paleontologists are reasonably imaginative, and quite early on, they came up with this really neat trick, and that's that in areas where you have ants in the fossil locality, you can actually pick up the debris formed around an anthill and look there for fossils. And the reason is that ants, they pick together, or some species of ant at least, they pick together particles of rock are about the same size. So they were basically having a natural way of concentrating these fossils. So paleontologists, paleontologists for a long time would basically be wrecking anthills around the world. But we thought we could maybe do better, and so we kind of put our heads together and just thought that, well, we can probably use the laser fluorescent properties of the fossils to make this kind of process less cumbersome, more efficient. So in this slide here, you can see that this part is fluorescing really well under the laser, and some other bones don't fluoresce as well. Different parts of the bones fluoresce with different properties. The actual matrix holding the bone, it can have different fluorescent properties. So the idea is the fact that things fluoresce or glow with different colors, well, we'll use that to try and find fossils. So we developed this sorting machine, and when you showed it to various colleagues, they kind of, they didn't faint, but it was kind of close to that. They were kind of, we managed to sort through fossils that maybe take 100 or maybe perhaps even 1,000 times faster using this method. So it was really kind of a nice step forward. So that's something that we're hoping will help with the rate of discovery in the field. Another bottleneck is actually preparing fossils. So I've had experience preparing fossils myself, but you really need to be extremely patient and very skilled to take them out. And preparing a fossil can actually take years and years to do. So that's a big problem if you're trying to kind of find something and want to work on it, and you're like, oh, when's it going to be ready? So we also managed to find ways of using the laser to help with that. And the specific property is as follows. So this is a portion that isn't fluorescing, and with the laser you can see that. What the laser can do in certain types of fossils is actually bring out the detail much more clearly, but more importantly can actually look a few millimeters into the rock. So it's kind of like a very shallow X-ray. So the implications for that is that normally when you prepare, the preparator has to basically rely on the tiny bits of bone they can see to know when to continue and not. So that's why it's such a skilled job. So with the laser, you have a way of kind of knowing if you're going to hit bone a bit kind of earlier than you would. So that should improve the rate at which we get prepare the fossils out for study. So really with the LSF, not only is it a way of kind of dealing with solving old puzzles in the field, you know, the origin of birds, the actual appearance and evolution appearance in dinosaurs, but actually as a way of eliminating or widening the bottlenecks that limit the rate of discovery in the field. So I hope you have enjoyed my talk, and thanks very much.